Good day, good afternoon, good morning, and good evening, everybody, and welcome to our fourth session of our coffee break webinars. Today, we will be covering one of our trap and treat technologies, so the BOS 200 and BOS 200 Plus. Together with me today, we have again Mike Mazariz from AST Environmental, one of our key partners with injections of the trap and treat technologies. A quick housekeeping as always. So what we will cover today is again the way that as ILSCOV and RPI group work with the trap and treat BOS 200 and BOS 200 Plus technology. We will look at specific case studies to put in perspective how the technology works and it's used from design to performance. We will of course allow time for a Q&A session. Couple of quick reminders. We will complete our coffee break webinar session on October 3rd, when we will talk about PFAS remediation together with our partners from SETCO at Mineral Technologies, which have a novel technique for pretty much implemented now for almost 8 years when it comes to PFAS remediation. At the same time, we would like to remind our presence as ILSCOV AST and also SETCO at Remtech Europe in next week from September 20th to 22nd in Italy, in Ferrara. We will have five presentations throughout 3 sessions where we will present different case studies from DNAPL and LNAPL remediation and also a bit about PFAS remediation. I'll leave now the word to Mike to explain a bit how we work with the trap and treat technology. And welcome, Mike.
Thank you, Giorgio. I guess one quick note on the conference next week. I'll actually be there in Ferrara. All of those presentations are going to be available via live streaming as well. So if you're interested in any of those topics, you can go and register at the website. So today we'll talk about, we've covered chlorinated solvent treatment. And so this is a sister technology that is activated carbon based, similar to all the other trap and treat products. But this one is specifically designed to remediate petroleum hydrocarbons. And so we're adding, besides the activated carbon, we're adding a suite of electron acceptors. So sulfate, nitrate, there's also some nutrients in there, as well as a consortium of facultative bacteria that are designed to degrade petroleum hydrocarbons. And so we add gypsum, so calcium sulfate, as you'll see there, as a long-term sulfate source. So typically we're looking at about an 18 to 24 month release window for the gypsum, and trying to keep those concentrations typically above 50 to 100 milligrams per liter. And so the idea, obviously, we're going to adsorb the contaminants onto the carbon, and then the bacteria are adsorbed onto the carbon. They use the electron acceptors to degrade the hydrocarbons. It opens up pore space within the activated carbon pore structure. And then the process continues again until the electron acceptors are at low concentration, which again is usually in an 18 to 24 month window. Next slide. So all the projects that Giorgio is going to highlight here in a few minutes involve what we call the remedial design characterization step, or the RDC. And this is a really kind of a unique aspect of working with RPI group that we bring. We have a laboratory here I'm based in Denver, Colorado, and here in the US. And we have what we call our project support laboratory is here in our office at the RPI headquarters. And it runs pro bono analytical for all of our projects globally. And what we use this preliminary step to do is really refine the conceptual site model. So we take the available data, and then we propose a certain number of additional soil borings, groundwater samples to help refine that model. And actually, Elskov has developed modeling software, which I believe you'll see shortly, that integrates that data very nicely in 2-dimensional and 3-dimensional views. But the strength or the power of the RDC process is really in two main areas. One is it helps us really fine-tune the design, but then it also really helps us set expectations, because when you're using limited or old soil data and groundwater data, you may not have a really good handle on how that mass is situated in the vertical column. And so it really helps us optimize our design, which in most cases ends up saving the client money, but it also helps us set expectations, because every technology has limits. And so if, for example, we feel like we're going to need 2 applications over the course of, say, 3 or 4 years to be able to meet the remedial objectives, that helps you and helps your client plan financially as from a total life cycle cost. So here's just a real quick example. This was a site here in the US, small UST site, where the original design that you see in the upper right was just based on a limited data set, just on 5 points. We went out and advanced 12 soil borings. It's all pretty shallow, so you can do all this work in a day, or maybe even a day and a half. And then we were able to take that data and subdivide the site for the final design that you see in the lower right, where we took it from 3 different treatment areas to 5. And if you look at the table in the lower left, you'll see our treatment area did increase a little bit, but because we were able to refine that treatment thickness from 1.5 to 6 to 1.5 to 3.7, we were able to reduce the product, field days, and the overall budget. So even when you include that RDC value, that 5750, we still saved the project a little over 20%. Next slide. And so lastly, from an injection standpoint, these are all slurries. So the BOS 100, CAT 100, BOS 200, the Fluorosorb, they're all injected using the same systems that you see there in Giorgio's photo. We inject these top down. We feel like that's best practice about every half meter or so. And top down is important, because when you're injecting slurries, if you were to do it in a bottom-up fashion, there's a chance that you're going to inject your slurry down into that borehole that you've just vacated. So it's really important, especially on a site with any sort of fine-grained clay or silt lithology, because that hole is going to stay open as you advance if you are doing it bottom up. So you have a chance of being able to short circuit that down into that borehole, and again, you're not getting that good lateral distribution that we need. So we always go top down, and the systems are very flexible from a flow rate and pressure standpoint, as you can see there. We're not going up to that 920 liters per minute. That's more for like bedrock applications. So on your typical gas station site, the flow rates are going to be the flow rates and pressures are going to be lower than what you see here. And then secondly, we use different downhole injection tips to be able to manipulate the exit velocity coming out. So by modifying your flow rate and modifying the number and the diameter of your injection holes that are in your injection tip, you can modify your velocity coming out. So for example, you need more velocity in a sand site than you do, say, a clay site, because you really, the sand wants to filter out the solid. And so we need to promote radial mixing. We need some more energy to do that. So Giorgio, anything that I missed on those slides?
I think you did pretty good, Mike. Thank you so much. And we will move on the next few minutes of our webinar to discuss a few case studies that we have performed here in Europe with the BOS 200 and BOS 200 Plus. We'll start from a performance-based remediation contract, which got us involved now almost 10 years ago with a major oil and gas client. They had a site that had been on their books for many years at that time, already like 10 to 12 years, pump and treat and soil vapor extraction, just couldn't do it. And what we started with was an RDC as we do on most of our sites to make sure that we had the conceptual model right. And we actually found out at that time that there was a key layer in the old geological settings that was missed out, which was this deeper weathered limestone layer that held a lot of actual contaminant mass that had never been properly investigated. And that kind of changed the name of the game when it came to the final design. We managed to put up a plan for the client that allowed them to maintain the station operational. As you can see, as Mike was showing from the other gas station example, we ended up having multiple designs for each of the areas that you see marked. So here we had A1 through A8, and including injections in between USTs, and then the remaining parts in the second half of the site. And this naming, for example, was given from a production standpoint for the client to look at partial, let's say, interference with some of the areas of the station. Ultimately, we ended up injecting in 287 points. We reached depth to limestone to about 12 to 14 meter, and we installed 72,000 kilos of BOS 200. The results from that site were pretty clear. What we had was the cleanup that we had to reach for the client, which was specific targets within selected wells on site, where we had to achieve a specific concentrations levels to be able to unlock performance milestones. And that was achieved over the years from 2015 to 2018, so pretty much over a period of 3 years. We had clear evidence of reduction of contamination into the well that was sort of the source area, representing the source area, where during the RDC we found 1.5 meter of LNAPL. At that time, the client asked us to do a short pilot test. That pilot test showed already that we could handle most of that LNAPL, but it was not designed for the full mass of contaminant. After the full-scale injection, which took place between Q3, Q4 of 2014 and Q2 of 2015, we then knocked out the final LNAPL present in the well, and the concentrations in this well in groundwater by the time of the no further action being granted were down to non-detect for benzene. A secondary objective that had to be met for this site was the cleanup of the limestone aquifer, because there was an artificial cross-contamination that had been created in the previous years by installing the pump and treat across both aquifers in the upper clays and in the lower limestone. We had separate wells installed before the remediation to clearly see the conditions in the limestone compared to the clay. The results from these wells are listed here, when we can see that until the start of the remediation, there was still benzene present in the groundwater aquifer. As the injections took place and the pump and treat that was temporarily moved towards the source of the site was discontinued completely, the effect of the injections took over, and we can see natural degradation occurring in the limestone to the point where we were able to close the case both for the upper clays and the limestone aquifer. We also took validation data that the client asked us to do to prove that we were truly degrading the mass in the soil and not just sort of buffering the groundwater concentration by use of carbon. And this data is quite clear. The soil data in the blue line comes from the soil core that was performed in the location where we saw that 1.5 meter of LNAPL. 3 years later, so we saw the effects of the pilot test by performing the same level of soil sampling 0.5 meter away from the original location, and we can see a clear pattern in the reduction of the total hydrocarbon concentrations. And we followed up with a third core 2 years after the full scale, performed again 0.5 meter within the original location, where we could see again the reduction in concentration in soil, showing how much the mass was being biologically degraded, but ultimately linking with the groundwater concentrations results that we were seeing in the wells. Here it's a quick example of the distribution at that site that we had also seen from the course that we did for validation. And as Mike was saying, you have different levels of distribution when it comes to silty formations, clay formation, and sandy formation. And here we have a nice one because we have a transition zone from sands into Copenhagen clay, which is fairly hard. And you can see how the distribution of BOS 200 is more of a turbulent mixing in the upper sands versus the tree root type of distribution in the clay formation. Similar, we have a couple of other cases which are quite nice from Finland, where at one we can see the output of the RTC through our modeling software. At this site, we collected 425 samples that were analyzed by RPI free of charge. At this site, we found a unique situation because we had 12 meters of dry sands, super homogeneous, and the problem at this site was actually the MTBE contamination that was leaving the site in the groundwater. So the authorities wanted a solution that was okay in leaving the soil mass in the upper sands untreated, but he had to do something about the groundwater contamination on site and ensuring that MTBE would not migrate off site. At this site, we actually perform a pre-drilling of the injection points to compensate for the friction that dual direct push would have been suffering in those dry sands. We prepared 100 injection points, which were performed, and the results of this remediation are clearly seen in this graph, where we could see the MTBE contamination at the compliance point constantly increasing throughout the 3 years leading to the injection, and then decreasing to the point where we were well below the requirement from the authorities over a period of roughly 2.5 to 3 years post injection. And this site was granted as well and no further action. In similar condition here, it's a site not far away from the one just presented, but we can see how important the RDC plays a role in how to define which kind of remediation you want to perform. And that means taking action in terms of looking at the existing data. So for example, this site, we had data from the client. We were given access to a little bit of budget to do an RDC. What the RDC led us to see was the presence of these dry sands where all the soil mass was linked to. But ultimately, the objective for this site in terms of remediation was different than the previous one. In this case, the client was facing an injunction because of the presence of an extraction well from the municipality just 3 meters away from their old property. So the authorities demanded cleanup of the soil. So what we ended up doing here was to estimate as good as we could the soil mass present in those layers where we found contamination. But in this case, we performed soil mixing. So the site was available because the gas station had already been fully demolished. We used that data to pile up soil in different locations based on the level of contamination that we measured. We blended BOS 200 plus with the soil and then relayered the soil coming back up. And here in the bottom corner, we can see how the gas station was left at completion of the works. We recently performed a validation at this site where we could see from the cores the clear presence of the BOS 200 mixed with the sands, and we can see the true contact of the product, enabling the biodegradation to happen a lot more rapidly actually than when we do injection. And the results led to the estimation of a much lower total soil contaminant mass for the compounds that we were asked to treat. And we could see a reduction of roughly 90% compared to the pre-remediation conditions, and also a reduction of the total contaminant volume left on site. This case is likely going to a closure as well, but this is just to show you how the remedial design, as I said, plays an important role in the final results. And lastly, a quick look at a coastal site where we got involved in Denmark in this case. Here we had an history of an old 35 cubic meter Xylene spill occurring at this terminal harbor. The spill had been pushing towards the marine environment, and the conditions pretty much 35 years after the spill, we're still showing LNAPL presence in many of the wells, and a clear issue towards the to the sea, to the marine environment. In this case, the client took action voluntarily, so they wanted to use budget as, let's say, reasonably as possible. In this case, for example, we didn't do an RDC. We used some existing data from groundwater only. We designed the remediation still in a sensible manner compared to the criteria we had to reach. And here we can see the results in groundwater, where in just roughly 2.5 years post-injection, we can see a clear reduction in the TPH concentrations, where we have on average in the two areas, so on site and out on the public beach, a clear trend towards the final criteria that we have to reach. Similarly, at this site, we have done a soil validation, and this as well was performed just a few weeks ago. Here again, we can see the distribution. This is a sandy formation, so we can see how BOS 200 has been distributed more as a turbulent mixing in the formation. We have performed a soil evaluation in terms of mass existing pre and post remediation. The client actually asked us to go a bit upstream, where they've never really done any validation, to see if there was any mass sitting upstream. But the ultimate result was that, again, we could see a 70% reduction in concentrations in soil from pre to post conditions, and how nicely the barrier here on site is working, even though we have about 1,000 kilos worth of contaminant mass pushing from areas that we hadn't been treating. We thank you for your time. We have the Q&A possibilities from selecting the Q&A bar in the from the bar at the top of the screen. Mike, any comment in the meantime while we?
No, I think that's a good summary. We have, if you're interested in sort of the previous webinars that we've given, those are posted or are available. Those have been uploaded to YouTube, and so you can reach out to Giorgio and or myself, and we can get you the link to those, as well as the AST website, which is the astenv.com. We've got a list about 24 project summaries for various contaminants that are listed. If you're looking for other sites than what was presented here. Looks like we do have one question. Yeah.
Yes, direct. Is it direct push the only possible technology to be used on site, or did you try test in some areas other injection technologies? So I guess one example that we showed, as I said, we could see how sometimes soil mixing can be a very efficient way of distributing the product in the best way possible. The example we show was with sands, but it can be done with clays, so by using a mixing auger and then using some stabilizing compounds like cement, lime, or just lime especially when we work in Scandinavia, we have those kind of scenarios where clay is fairly soft. So if you do a mixing of the clay, then you definitely need some stabilizer at the end to suck up a bit of the extra moisture that you have created and generated in the soil. Mike, I guess from your side in the US, you've seen a bit of everything.
Right. Yeah. So I would say direct push by far is the most common. Whether you need to use that pre-drill that Giorgio mentioned, when we can't use direct push, but it's not consolidated, it's not bedrock. We can pre-drill the locations and backfill those with bentonite, and then re-drill those with direct push. And then there's bedrock as well. That's so when you're in consolidated geologies, we can use packer systems. And then lastly would be the soil mixing, and that really comes in two different two different flavors. The one that Giorgio showed, the site in Finland, but then also you can also trench the product in as well to create reactive barrier walls, which is another application that really wasn't touched on here today, but we do quite a bit of PRB applications with these technologies, sometimes used in conjunction with source treatment, sometimes not. Maybe the source is not available. If it's, say, an existing site operating UST, for example, and the goal is to just limit the flux of the dissolved contamination leaving the property, we can either inject or trench that product in a PRB configuration. So tight spacing, all in, say 3-4 meter sort of section wide. We can install the product that way to be able just to limit that flux of the dissolve phase.
Yeah, and I think one important aspect to mention is also the type of slurry that we use. So when we give out proposal, I mean, generally one question we are always asked is, can you inject your product through monitoring wells or injection wells or things like that, screened wells? And when you think of the configuration of the slurry, so you have a solid material with an okay particle size, you would not want to have an external filter to kind of interfere with your distribution. So the reason why direct push becomes very efficient is that you allow the distribution of this solid material in the best way possible without any artificial, let's say, interference. And when you think of dissolved products, something that dissolves in water, then of course the distribution would be different to assess. The beauty, I think, of our technology is that once they are installed, and they stay where they are installed, and they are not going to move with groundwater. So you have an installation that the client buys, and it's like an insurance. You know that what is purchased is there on site, and it will continue working for many years to come.
So I guess, one question, and I mean, I think it was in some of these, it may have been, I think it was in there in the original sort of application slide, Giorgio, but, I think it's good to mention what the expected radius of influence is. It sort of ties in with what you just mentioned. And typically, we're, about, 1.5 to maybe maximum 3 meters spacing between the injection points, and that's going to be a function of lithology, but also what your groundwater table depth is. So the shallower the groundwater table, the tighter the injection spacing needs to be, and then as you go deeper, say 3, 4, 5 meters below grade, then you can expand that spacing out and do 2 to 3 meters between injection points.
I think I don't see any more questions coming in at the moment. So I think for once we are managing to stay within the 30 minutes window, which is always good. But yeah, again, a reminder about the last webinar regarding PFAS, which is fairly interesting, because we will show what we can do with a product that is actually not based on activated carbon compared to our strength with the RPI group, because we know sometimes that despite activated carbon being a beautiful product, there are specific contaminants that sometimes do not like activated carbon as others do. Will be quite interesting. So we welcome again any questions you have to our email addresses, and wish to see you again on the 3rd of October for the last session. Thank you, Mike, for your time as well.
Thanks, Giorgio, and thanks everyone for attending.
Thank you.